In this video, we'll be looking at various statistical concepts. The mean time between failures is an indicator of the average length of time a product will operate for until failure. It is created by running multiples of the same model until failure and then averaging the data. A 5-point summary gives information about a sample set's median value, lower quartile, or the median of the lower half of the set, upper quartile, or the median of the upper half of the set, minimum and maximum points. This information is visually presented as a box and whisker plot. Outliers are considered as data points which are distanced from the main set. Here we see outliers in both a distributed set as well as a set that conforms to a trend. Outliers are often excluded from the sample set before proceeding with statistical analysis. They are often attributed to data collection errors, meaning that they never belonged in the set in the first place. Outliers also tend to skew the data set's mean average and spread. We can see why when we compare the mean and standard deviations from a raw dataset which contains outliers to the clean dataset in which the outliers have been removed. Compared to the clean data, we can see that the raw data's mean is pulled in the direction of the outlier. The raw dataset's standard deviation is also increased as the outlier is located far from the mean. Scatter plots show whether a relationship exists between two datasets and what that relationship is, linear, exponential, or otherwise. There is a relationship between a motor's torque and the frequency that it's running at. We can see this relationship when we plot the two datasets against each other on a scatter plot. Correlation is a measure of the strength of the relationship which exists between two sets of data. As in the case of the motor's torque to its frequency, a positive correlation shows a defined positive gradient when plotted. The correlation coefficient lies between 1 and -1. It's a measure of linear correlation. We will go into how to calculate the coefficient shortly. A high negative correlation occurs when there is a strong inverse relationship between the two datasets, or when as one dataset increases in value, corresponding points in the other dataset decrease. You would expect a correlation coefficient close to -1 in this case. No correlation, and hence no relationship between the datasets, is seen when the scatter plot shows a random distribution with no defined trend. This would yield a correlation coefficient close to 0. It's important to keep in mind that correlation doesn't necessarily imply causality. The frequency-torque relationship of a motor is most definitely a causal one and can be backed up by equations explaining why this is the case. On the other hand, take a look at this scatter plot. It's derived from real data and shows a strong inverse correlation between US road fatalities and metric tons of lemons imported from Mexico. You would have a hard time convincing anyone that importing more lemons from Mexico decreases the number of road fatalities in the US, even though the data seems to suggest so. The correlation coefficient is calculated using this formula, where n is the number of samples in each set and s, x, or y is the standard deviation of each dataset. We won't go through the standard deviation calculation as this is covered in another video. We will now look at how to apply this formula to the motor scenario. I have put the data into a spreadsheet. Spreadsheets allow us to apply formulas to entire datasets with ease. In the green row, I have calculated the mean of each dataset. In columns 4 and 5, I have negated the respective means from each of the datasets as is required by the formula. In columns 6 and 7, I have divided columns 4 and 5 by their respective standard deviations, which have previously been calculated and listed in the blue row. I have then multiplied rows 6 and 7 together to create row 8, which I have then tallied up and shown in red. Finally, I divide this number by 1 less than the number of samples in each set, and I've calculated the correlation coefficient to be 0.84. This indicates a reasonably strong positive correlation. If the motor's frequency goes higher than its rating, the torque drops. We can see on the scatter plot that this is the only point we've taken which doesn't conform to the prevailing trend. If we were only interested in the torque-speed relationship below the motor's rating, we could consider the last point an outlier and remove it from the set, which we will. Going through the same motions as before, we end up with a perfect positive correlation coefficient of exactly 1. Now that we have established that there is a defined positive trend between our motor's speed and torque, we want to know exactly what that trend is. We do this with a method called regression. With this particular case, we're looking for a linear trend, so we will use a linear regression calculation. Our regression calculation will output a line which best fits the trend seen on the scatter plot. Linear equations take on the generic form of y is equal to mx plus c. Linear equations specify the rule which connects one set of values, which we will call x, to another set of values, which we will call y. The set of x values lie on the horizontal or x-axis of a graph. The y values lie on the vertical or y-axis. Our line can be characterized by two things: its steepness, or gradient, and its position, given by the point at which it intercepts the y-axis. You can see that using a combination of steepness and position allows us to describe any straight line in the two-dimensional plane. In our equation, the gradient is m, the coefficient of x. The intercept is c, which we can see is added to the x term. As we're considering our regression line to be straight, the equation will take the form of the generic linear model. We will use this formula to calculate the line's gradient. By applying a substitution of the mean averages of the datasets into the regression line, we can locate the y-axis intercept. For the gradient calculation, we again require a spreadsheet as we are performing calculations on the entire datasets. I've started in the same way as before, creating columns 3 and 4 by negating the respective means from the frequency and torque datasets. I then create column 5 by squaring column 3 and create column 6 by multiplying columns 3 and 4 together. I then create a summation of columns 5 and 6 and divide the summation of column 6 by the summation of column 5. To get the y-intercept, I use the fact that the mean averages of the two datasets form a pair of coordinates that fall on the regression line. I substitute these points into the formula, and as I now know my gradient, I can rearrange the formula to solve for c. Here is the regression calculation for the outlier adjusted set. You can see that it perfectly passes through each point, as would be expected for a trend with a correlation of exactly 1.